Hello everyone, my name is Benson. I'm a PhD student at the Hasso Plattner Institute in Potsdam, Germany. And today I'm going to present our work, Darwin, Scale and Stream Processing, which is work done together with my supervisor, Tilmann and Rabl. So yeah, before we dive in, let me quickly just give a recap on in stream processing, some of the terminology we're looking at. So in stream processing, we kind of want to process an infinite data stream. You can see here blue tuples coming in, there's some stream processing engine at the end. We want to have some output. So currently there are two main ways to achieve this, or two system designs that process data like this. So one is called scale out stream processing systems. So in this case, the main idea is if we have large data volumes, then we just use many servers to process incoming data. And the main focus of this hardware is just commodity hardware. So we'll just use off-the-shelf servers or some small instances on the cloud. And if we need to handle more data, we'll just add more servers to process this. And some very prominent examples of this are Apache Flink or Spark Streaming, which I guess most of you are aware of. On the other hand, so this is something more widely studied in academia, we have scaled-up systems. And the idea here is to handle large data volumes, we just use really big servers. So high-end servers, like a lot of NUMA awareness in there and some optimizations regarding this to process a lot of data very efficiently. And some examples here of like Streambox, Grizzly or Sabre, in case you've heard some of them. So now I've presented scale up and scale out designs, why do we need scale in? And let me start with an example for this. So Alibaba had their Singles Day just over a year ago, which is a massive shopping day in China. And on that day, they processed up to 4 billion records per second on their Apache Flink cluster. Apache Flink is a scale-out system that's very widely used in industry. And to handle this data load, they processed this stream on 1.5 million CPUs. So just to give you a small example, the exact configuration is not known, but just as a ballpark idea, we calculated something with a 16-core instance that you can get on Alibaba's cloud for like $1 a day. And to process this data, then they would need more than 90,000 virtual machines. And this alone in nominal infrastructure cost would be $2.25 million a day. And if we look at the numbers exactly, this amounts to only about 42,000 events per second per server, which doesn't seem that much. So now on the other hand, we have more modern scale-up systems, for example, Grizzly, which was recently proposed at SIGMOD, which is a scale-up stream processing system. And in this paper, the authors present a system that can achieve more than 100 million events per second on the single server. And yeah, if we do the same calculation, again, a bit oversimplified here, we take a 52-core instance, which costs around $6 a day on Alibaba's cloud, and we can run this entire thing on 40 VMs for less than $6,000 a day. So we can see there's a huge contrast in what is currently done, for example, at Alibaba, and what academia proposes on the other hand. But it's really important to note at this point that this is simply not possible with what's presented in research. So processing 4 billion events per second is worth multiple terabytes of data. And currently it's just simply not possible to ingest this into a single server. And even with this, we can see that Grizzly would need 40 VMs to handle the load. And this system is designed for a single server. So let's have a look at existing systems and what's out there. And we can really see the strong contrast between scale-up and scale-out systems. So here we look at traditional scale-out systems, so again like Flink, Spark Streaming, and they're widely used in industry, and so they kind of have a lot of features that are really relevant for industry and their application there. So they would support in-memory and larger than memory state, with also persistent state, so that makes them recoverable. They have checkpointing mechanisms and all this. But you can see on the right, the hardware resource efficiency these systems offer are not that high or very limited. And on the other hand, again, a lot of the stuff from academia, we have these scale-up systems, and they have a strong focus on hardware resource efficiency with various techniques to improve this. But you can see all the state is processed in memory, and if the system crashes, data is lost. So this really puts users in this tight spot to decide what they need or what they want. So, for example, they say they want to choose a scale-up system, then they really get a lot of performance. You can see they can process hundreds of millions of events per second, but if the system crashes or the application crashes, then data is just lost. And in stream processing, if we're processing large amounts of data over long periods of time, this might mean we need to reprocess weeks of data or maybe even or days or whatever. On the other hand, we have scale-out systems, and they really offer availability, and so this is why they're also very widely used in industry. But all of these systems are quite inefficient, so there's quite a few studies that show the inefficiencies of scale-out systems, mainly related to their designs and the operator designs they have and them being in Java. And just one important fact also, again, if you want to choose scale up, but your use case just simply doesn't work on a single server like the Alibaba use case, you're kind of stuck automatically with scale out. So there's no real option here. So to overcome this choice that users need to make, we propose scale-in stream processing. So like I just mentioned, we have scale-out systems and we have scale-up systems, and both of them have like this one-dimensional focus. So in a scale-out system, to process more data, we need to add more and more servers, but the individual servers largely ignore the hardware that's used inside the servers. And the scale-up system will focus a lot on the hardware, but it usually focuses on high-end hardware. And if we want to process a lot of data, our server can handle this, we need an even larger server, and at some point this doesn't scale further. So what we really want to do with scale-in processing is actually really focus on the hardware that's given. And this can be high-end or low-end hardware. Just in general, we want to focus on all hardware. It's really time to focus on this. So if you have an SSD, we fully want to use that. If you have persistent memory as a new emerging technology, we want to focus on this. If you have only in-memory processing, then we want to be fast on that. This applies also to network. If you have slow Ethernet, if you have fast Ethernet, if you have RDMA, it's all about really using what's there. And so let's say you have a certain SLO, you want to process a certain amount of data per second, then we don't want the system to limit us on that choice, but we want to say, okay, this is what I have. What kind of configuration, what kind of setup do I need to achieve this? So a scale-up system or scale-out system, they will kind of limit you in the setups you can use. So just using beefier servers in a scale-out system will probably not be beneficial because the bottlenecks are somewhere else. And using a scale-up system, kind of if you're stuck on one server, you can't add more servers. So a scale-in system really allows the user to choose the system and stick with the system without having to switch in between, but just add different configurations or adapt their server configurations in the meantime, depending on their use case and need. So what needs to be done so we can build a new scale-in system? And for this, we identified a few challenges that current systems have, so be it scale-in, scale-up or scale-out systems. So the first of which is just general resource inefficiency. A lot of scale-out systems just have really low CPU network and memory bandwidth utilization, and there's some studies out there that show why this is the case. Often this depends on the operating model they have, and also a lot of has to do with the Java systems they run in. Another general issue we have encountered is that stream processing systems don't have the same level of system optimization that we know, for example, from databases. So database will often be tuned to the underlying hardware or system specifics, and we just don't really see that in stream processing systems to that level yet. So there's a lot of potential. And the third one in general is state management. So often these systems will ignore modern storage technology and also often fall back to general purpose key value interfaces to store the state, kind of ignoring streaming specific state access. So I won't go into all of this in detail in the following slides due to time reasons, but we really encourage you to read the paper for more information on this. Let's look at a few specifics on how to overcome these challenges. So first of all, this is tackling general resource inefficiency that we saw as the first challenge. And for this, we kind of really want to adopt a concept that has been used in databases for a while now, which is query compilation. So we can see here on the side, on the left-hand side, this is a basic operator graph. And in the classical iterator model that a lot of stream processing engines still employ, we have these operators and they just call next on the previous operator. And in this design, we have many virtual method calls and bad cache locality. There's a lot of research in this in databases. And then more recently, this trend is kind of also coming to stream processing engines, for example, in Grizzly, which was recently proposed at Sigmod, where we kind of invert the control flow and then we generate the query for the actual need we have. So in this case, we iterate over the source data, we perform a filter, we perform an aggregation, and we ship the data further on. And in this, we have little to no virtual method calls. We have really good cache locality on the data. And recent work has really shown this is very, very promising to achieve high performance, also very high CPU utilization, and also better memory bandwidth utilization. Another issue we want to look at is tackling state management. And for this, we propose using modern storage devices. So as I mentioned before, scale-up systems often will perform computations only in memory and data is lost. So this is represented here by TBB, which is just a concurrent in-memory hash map, which is used in some recent scale-up systems. And RocksDB, on the other hand, which is persistent key-value store, which is used in, for example, Apache Flink. And then here, in this case, we're also looking at Viper, which is a novel hybrid PMEM, also persistent memory key-value store, which we presented at VLDB last year. And we can see with this persistent memory option, we achieve very close to DRAM performance, while offering, first of all, larger than memory state and also persistent. So in case of a crash, we've also covered that kind of case. And we can really see here that it's time to rethink slow persistent storage. So persistent memory in this case, as a high-end storage device, really achieves very good performance, but also NVMe SSDs, one level below that, have been shown to achieve very good performance in recent work. And also in general, this kind of allows us to design novel streaming-specific state management backends over just generic key-value store interfaces that have often been used in previous work. So yeah, that's it from my side for today. If you have any questions, please feel free to reach out to us. Here are the emails on the right, or we're outsiders, so feel free to speak to us here. I also encourage you to read the paper for more details. This is very early ongoing research, so we're really open to discussion. We'd really love to hear your thoughts on some of the ideas and some problems you may be facing, or some ideas on how to improve this. Thanks for your attention, and now I'm open for questions.